Okay, we are discussing the situation where we have more than one atoms in a unit cell and how tight binding method works there, and we showed that the tight binding still works, Bloch theorem still works. All that you have to do is to replace your scalar elements, the scalar matrix elements which are just single elements, by a matrix of the dimension of the number of atoms in the unit cell. For example, in a 2 by 2 unit cell, if each atom is contributing one orbital, then you have a 2 by 2 Bloch matrix that replaces your scalar for the one atom per unit cell case. But the complications are not too much. It's the procedure is the same, and instead of scalars, you have to just handle instead of just complex numbers, you have to handle with a 2 by 2 or n by n finite dimensional matrix. That is all. So, so that means we can now take up the case of graphene, for example, and for graphene, let me just draw the graphene unit cell. It is drawn already on the on the screen. So, what I will do is that let me just try to draw it again for my convenience. And so on. I will have to draw one more. Okay. So, my there are these two inequivalent sides. So, there is this circle here and cross here, circle here and cross here, circle here, cross here, circle, cross, 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 circle, and so on. Okay. And I choose my primitive vectors, and these two I call them A1 and A2. Okay. Remember, these the cross and the circle do not represent two different kinds of atoms in graphene. So, they are both carbon, but they are at inequivalent sides. So, as we discussed the other day, we have to choose unit cells which are kind of these are the unit cells, two combination of two in the left hand side, that the yellow region is the new unit cell. So, that is what the red and blue are the two inequivalent carbon atoms, and that is exactly what I am doing here. Okay. So, then I just do, I have to just write down this A1 and A2, which I do. If this distance is A0, which is fixed distance for graphene, we can then write down A1 as x along x direction root 3 by 2 A0 plus in y direction root 3 by 2 A0, and A2 is again x 3 by 2 A0 minus y hat root 3 by 2 A0. My x and y are these two axes, x and y. x hat and y hat at the unit vectors along these two directions, as conventionally we do. Then we have this Hamiltonian matrix here, is very simple. Here remember that the hopping T 1 and T 2 are taken to be the same. So, they are remember this hopping T 1 was inter unit cell. So, between the blue and the red, and the T 2 is between two different unit cells, but that distance is the same as this one, right. So, if you look at this blue to red in the same unit cell, the hopping is the same as that blue and this red in a different unit cell. So, that this one and this one and this one belong in the same in the different unit cells, but their distances are the same and they are compared to the distance of the next the red one in the same unit cell. So, the hoppings T 1 that we considered minus T 1, the values T 1 and T 2, they must be the same. So, T 1 must be equal to T 2. So, for graphene life becomes simpler, much simpler actually, in this that the T 1 and T 2 are the same. So, that immediately tells us that gap will vanish in certain directions. So, let us that gap can vanish in certain directions. So, let us just look at this Hamiltonian matrix, which is again as we did in the previous case, is equal to epsilon naught then minus T 1 minus. So, let me just T 1 and T 2 distinction I do not make, it is write as T minus T e to the power I k dot A 1 plus minus T e to the power I k dot A 2. Similarly, just the Hermitian conjugate of that. So, minus T e to the power I k dot A 1, the minus sign, minus T e to the power minus I k dot A 2 epsilon naught. So, this is the matrix. You can put minus I k here, minus I k here and plus I k here, it just does not make anything different. It is just your choice of how you took your directions and unit cells and choose your beta transpose matrices. But all you have to do now is to diagonalize this matrix. This diagonalization is already done in literature. You will find it, or you can do it yourself. It is straightforward. You will find that the energy has a fairly long form T root over 1 plus 4 cos root 3 by 2 A naught k y into cosine 3 by 2 A naught k x plus 4 cosine square root 3 by 2 A naught k y. So, all the terms are under the root. So, that is the energy and so what one now does is that one goes to these points in the Brillouin zone. So, I leave it for you to check, and it is all available everywhere, but I would urge you to do it for yourself. Go to these points k and k prime, find their coordinates in the first Brillouin zone, and put those kx and ky values here at for take it k point, it has a, you can see that it has a kx and ky, and the k prime is basically kx and the same ky with a minus sign. So, so these 2 points you can check, and you can actually check in every of these 6 points. These are all equivalent points. There are 3 points which are like k, 3 points which are equivalent to k prime. So, at all these points you will find that this thing will give you a 0, and provided of course you choose your epsilon not equal to 0, and so this is a case, this is what we have shown here. Remember that these are these k and k prime points where the spectrum is gapless. At, and you can also check it at m point, you will find that it has the largest gap in the spectrum. You can do it in a computer or you can do it by hand. The interesting thing to do is to expand this band structure around the point k and k prime, where this term in under the root vanishes. So, so choose epsilon not to be 0, and then show that E equal to 0 at k and k prime points in the Brillouin zone. So, that is an exercise you can do, and the other exercise which is a bit more complicated, but you can still do it, is to make a Taylor expansion, for example, about that point, take any point k or any point the other or the point k prime, make a Taylor expansion of this Hamiltonian, and interestingly what you will see is that the Hamiltonian has a form which is very similar to a massless Dirac fermion form of a massless Dirac fermion, which is Hamiltonian will turn out to be sigma, will be some constant into sigma, some constant sigma dot k, k is the momentum. So, and this is the massless Dirac form with a linear spectrum, and sigmas are the Pauli matrices in 2 dimension. So, 2 by 2 Pauli matrices, you can you know that what these are, these appear in our problems of spins and all that. So, that is the kind of matrix, the matrix Hamiltonian that you will get for the for this this system if you expand about k or k prime point. So, these are like massless Dirac fermion. And that is a very important discovery, in the sense that this was actually worked out in before 1950. So, and it was after graphene came into being, it was discovered by, it was actually isolated by Geim and Novoselov, and the interest in graphene came back and people started working on it, and then of course, they saw that there is a Dirac spectrum at these points, and that spectrum is extremely important. So, look at this spectrum as I just showed, that these are 6 points where you have a you have nodes, the 2 spectra, the antibonding and bonding bands touch each other, and by the way, in graphene, this one orbital that we are talking about comes from the pz orbital, which is the pi orbital. So, in the carbon atom, and so they are out of the plane, okay, along the z direction, and their overlap gives rise to this band structure. So, here is the band structure along 3 different directions, the lower curve, lower picture, and you can see that at this point k there is a linear spectrum, just like a V. So, the 2 bands meet here like a V, but away, as you go away from the point k, you can see there are deviations So, that means the linear in K spectrum works only close to the point K or K prime or their equivalent points in the Brillouin zone. So, that is something one has to remember. So, this is the band structure for and other materials. For example, I just wanted to show you that it is always plotted along certain symmetry directions in the Brillouin zone. So, this is for example, some gamma x direction, gamma L direction, and for silicon, germanium and tin, it is the band structure is always plotted along certain symmetry directions, and 0 is conventionally taken as the Fermi level. So, the that as we did this epsilon naught was set to 0, one just sets the 0 of the scale to energy scale to at the Fermi level. So, Fermi level is at 0 energy. In most of these figures, that is what you will find. Okay, so let me show you how actually these plots are done. Fermi surfaces are plotted. So, let me show you a few examples of Fermi surfaces. For example, this is something that we were discussing the other day. It is a 2-dimensional square lattice. So, the tight binding model. So, this is Fermi surface. For example, this is square lattice. Now, this is the Brillouin zone. So, these points at the points at the extreme, this is plus pi by a, this is ky equal to pi by a, and this is minus pi by a in kx. So, this is pi by a 0, this is 0 pi by a, this is minus pi by a 0, and this is 0 minus pi by a. Okay. So, these are the 4 corners. Now, let us look at this gives you the Brillouin zone. So, let us start for example, this equation for example, this epsilon naught, which is written as E naught here, is so is taken to be 4 for example, delta E is let us not bother about delta E. So, E naught minus delta E is our epsilon naught. So, that epsilon naught is taken to be 4 in this expression. Okay. So, epsilon naught is not set to 0, but it really does not matter at all. So, we start our set of our energy starts from 4. So, you can see that minimum of energy is these 2 cos kx and 2 cos ky will give you minus 4, that is the minimum possible. So, 4 minus 4 will be 0 and maximum will be these cos kx and cos ky are both minus 1, and that will give you plus 4. So, that will be 4 plus 4 equal to 8. So, these are so the band goes here from 4 energy 4 in some units, you can call it EV or whatever, you do not need to mention the units at the moment. In some unit it is 4 and it goes up to 8. So, that is the usual way theoreticians or even an experimental paper will write the Fermi surfaces, because as I said, these energies are set to certain units, certain values. T for example is set to 1 here, for you can see A, which is the lattice constant, is set to 1. All these can be restored to get the real numbers for the proper correct lattice. Okay, so, this band basically goes from it goes from 0 to 8. So, this is 0 is the minimum of this band and it goes all the way up to 8. Okay. remember if you look at your expression, remember E equal to epsilon naught minus twice T cos k x plus cos k y for a square lattice. This is a 2-dimensional square lattice. So, this is the tight binding band. So, T equal to 1, epsilon naught is chosen to be 4. So, your bandwidth as we mentioned the other day has to be 40 80. So, that is exact. So, here is for example, it goes from minus 40 to plus 40, right. Minus 40 is minus 4, but there is a plus 4 here already, epsilon naught is set to plus 4. So, minus 4 plus 4 will give you 0 to. So, that is the band minimum here, and the plus 40 will take you all the way up to 8. So, 8 is the so 8 T is T becoming T being 1 is the bandwidth. So, all the bands are within this anyway. So, that is that we had done earlier. Let us look at how to calculate, how to do the Fermi surface. So, these are Fermi surfaces for different values of E. For example, see this E is basically controlled by the filling. So, number of electrons you are putting in. So, that is called the chemical potential or the Fermi energy. And so for example, for low filling you have almost a circular Fermi surface. So, that is the highest occupied level. This circle is the highest occupied level. Okay. So, that is for low filling, this happens. As you increase the filling, your E goes up, and you are going, first of all you are going up towards the zone boundary, which is this blue line, and you are also becoming distorted from the circular shape. In 3 dimension it is like a spherical, at low densities you have a spherical Fermi surface, and as you increase the Fermi surface becomes more distorted from a sphere. Okay. So, let us go on, and at you can see at 4 E equal to 4 you hit this blue line. So, this entire first Brillouin zone, which is this entire region under this square given by this blue line, is completely filled up. So, that is where the bands, the first Brillouin zone gets filled up, that is the half filled situation. So, all the states here are filled up, and so the Fermi surface is like a square. Now, this kind of flat Fermi surfaces, which is here is Fermi surface is a line here, it is a rotated square, and this blue square, the blue line, the perimeter of this square is your Fermi surface. Okay. Fermi energy is 0, this energy here is 0, as you just put E equal to 4 and you can check that the energy here is 0. So, this is the half filled Fermi surface, and the Fermi surface has flat regions which are lines here. In 3 dimension they will be like flat surfaces. Now, when you have flat regions in the Fermi surface, you can actually check for yourself, the density of states becomes extremely large, very large, because the density of states is actually proportional to the inverse of the gradient grad k of E. So, the derivative of E with respect to k, its inverse comes inside an integral to calculate the density of states, and that see if you have a flat region, the derivative goes to 0, and then you are really so basically it means that if you change k, your energy does not change, your energy just remains at a particular value, which is 0 here, E equal to 0, and nothing. So, that means that there are large number of states at that energy, because you change your k slightly, but your energy does not change. That means there are lots of k states in that at that energy, and this kind of Fermi surfaces are prone to distortion. They do not survive much in real crystals. This is a topic of course physics beyond this, but this is physics beyond single particle, and in the sense that you need an interaction, a scattering between these Fermi surfaces to make these Fermi surfaces unstable. And in real systems, this is always, most of the times happen. The system distorts either structurally or magnetic, forms a magnetic order, so that this kind of Fermi surface with flat regions which can be brought onto one another. See, if this Fermi this line can be translated, can be brought to the opposite blue line by just translating with a vector which is the reciprocal lattice vector of this of the Brillouin zone. So, such cases the Fermi surface is very unstable. So, these are instabilities of Fermi surface that are commonly encountered. These singularities are often called the Van Hoff singularities. They appear in many solid state properties of solid systems, of crystalline systems, at some specific fillings densities, where this the Fermi surface becomes this kind of flat becomes flat, and one region can be brought to the other by translating with a vector in the Brillouin zone. Anyway, so that is just to mention certain interesting things. The other thing that I wanted to I emphasized earlier was this form of this 2 electron band structure, 2 electron per unit cell band structure. Now, as you can see, suppose suppose we started. So, let me draw it again. So, let me just show you a bit more of this different Brillouin zones for square lattice. So, this is a this is the first Brillouin, blue one is the first Brillouin zone, the pink one is the second Brillouin zone, the greenish one is the third Brillouin zone, yellow is the fourth Brillouin zone, and so on. And look at how the Fermi surface now looks. It has gone beyond the first Brillouin zone, because your filling is such, your density is such that the Fermi surface has gone beyond the first Brillouin zone. Now, look at this red, this ring which is the Fermi surface. So, now you have to bring it to the first Brillouin zone in the reduced zone scheme. So, what you will do? You will just translate these red regions it was here on top, that red region has been translated here by a translation of a reciprocal lattice vector. This red region at the bottom has gone up to here at the top, and similarly this one on the left has gone to the right, and the right one has gone to the left. So, the right one has come here, the left one has come here, the red regions, and that is how the prescription to draw a reduced Brillouin zone, they draw the Fermi surface in a reduced Brillouin zone scheme works. Or you can draw any E versus K graph, bring it to first Brillouin zone. So, the Fermi surface actually now looks like in the reduced zone scheme, this is how the Fermi surface looks like on the right hand side. Although in the extended zone scheme, it has gone beyond the first Brillouin zone, entered the second Brillouin zone. So, these are other Fermi surfaces for cubic lattice at different fillings. Here you can see that the Brillouin zone has crossed the first Brillouin zone. The Fermi surface has crossed the first Brillouin zone and become open. This is called open Fermi surface in these regions where it has crossed the first Brillouin zone. So, these are other Fermi surface, BCC lattice, FCC lattice. These blue lines are the primitive vectors. So, these are there are databases. This is a database for Fermi surface for different elements in the periodic table. You can look up if you like. They are very complicated looking, simply because they have been all translated into the first Brillouin zone. So, they become sometimes they even become disjointed. So, one part of the Fermi surface is completely separated from the other part of the Fermi surface. So, that is possible, and that happens, and that has consequences in solid state physics. The thing that I was mentioning was that we were discussing this the formation of this band as there are these two bands. Now, it happened when you had this kind of a lattice and so on. But suppose I started with a lattice which is this the regular one atom per unit cell at a regular distance, say A. Now, as we just saw that this kind of a structure has stabilized its energy by bringing one band down and filling, in the half filled case, filling up the lower band and gaining a lot of energy. So, it is possible that if I can distort this bottom lattice, this lattice in such a way that it looks like this, then I might gain a lot of energy, and that actually happens. So, in low dimensions 1 and 2 dimensions, with the help of electron phonon coupling, electron lattice coupling, this kind of arrangement, this regular arrangement can go to an arrangement where one of them moves to the left or right, does not matter, and forms a 2 atom unit cell. And this kind of distortions do take place at low dimension systems 1 and 2 dimensions, and these of course, it requires electron to couple to phonons, and that kind of a calculation has been done. It was done long back by Rudolf Peierls. It is called Peierls distortion, where it is shown that in one dimension it is hard to form a regular crystalline lattice. It is prone to dimerization. This kind of one atom shifting towards closer to another atom alternately is called a dimerization. And this is one instability that you can see now that the Fermi surface is gone. The Fermi surface, there is no state at 0 energy. There is a gap at the Fermi level, which was originally the Fermi level for this one, for this lattice. There is now a gap that has opened. One set of bands have come down, and the system has gained a lot of energy by doing this. Of course, distortion also costs some elastic energy, but that cost is in lower dimensions, it is less than the gain you have in electronic energies by doing this dimerization. So, it was shown by Peierls that in low dimension systems, the system is prone to basically destroy its Fermi surface. It opens a gap, and this is again a Fermi surface instability, and this class of distortions are generally called Peierls distortions. We will not discuss it more here, but it is just to show that there are instabilities of Fermi surface.